In this video, I'd like to just take a look at another bootstrap hypothesis test example involving one population mean mu. So in this case, we have a consumer group, and they're concerned about the mean fat content of a certain grade of steak burger. They submit to an independent laboratory a random sample of 12 steak burgers for analysis. The percentage of fat is recorded here, and the manufacturer claims that the mean fat content of this grade of steak burger is less than 20%. Okay, so the alternative hypothesis in this case is the claim, right? What we're trying to test. So we're trying to test, is he right? Is the mean content less than 20? Well, our null hypothesis is that it is 20. So we just want to test to see if he's right. Is his mean content really lower than 20? Well, as you know, we assume the null is true. Okay, well, one layer that we're going to add to this is the idea that we believe that the sample is random, and so the sample behaves like the population. Sample behaves like population. Now, what do we mean that it behaves like the population? We mean that it has similar variability. Similar variability. Meaning that on average, if we look at the means, we'd expect them to be spread out a certain way, just like the population. So what we're going to do is we are going to simulate the null hypothesis. Simulate null hypothesis. And the way we're going to do this is we're going to say shift sample values so that the mean of the samples, so that mean of samples, or mean of means, is at mu. Okay, so how do we do that? Well, it's fairly simple. First of all, we need to compute what our mean is, and I've already done that here. The mean of this data set is 19. Okay, so x bar is equal to 19. And what I'm going to do, and you can do this any way you'd like, I'm going to open up a spreadsheet here real quick because that's going to be a faster way for me to compute this. I'm going to record my data values here. Actually, no, I'm sorry, I'm not going to use this. I'm going to use RStudio to do this. But basically what I want to do is I want to shift all of these and preserve their variability, meaning I want to make sure that they're still just spread out, that in other words these two values are still 6 units apart, but that the center of these values is at my null hypothesis, which is 20. Right now we're trying to test, is this significantly smaller than 20 for us to be able to say, we believe the whole population has a fat content of less than 20%. Remember, we're going to expect some variability from sample to sample, so based on what we observed here, is this enough to say, oh yeah, these burgers have less than 20% fat? Or do we conclude, yeah, we don't really have any belief to say it's any different than 20? Okay, so what I would do is I would first of all figure out what the difference is between my x value and my mean, right? So for example, I know that 21 is 2 units above, that's a +2. 18 is -1 units below. 19 is 0 units away from the mean. This is -3. This is -1. This is +5, excuse me. This one is +3. This one's 0, 5, -5, -1, and -4. Okay, so we know that if we add up these deviations right now, we get 0. Okay, well what we're going to do is we're going to add this to the null hypothesized mean value, because what that'll do is it'll preserve how spread out these values are. Like this value will still be 1 unit below the mean, because we'll take x minus x bar is -1, -1 plus 20 is 19. Similarly, 16, which is 3 units below the mean, if I do -3 plus 20, that just gives me a value of 17, which still says, relative to 20, it is 3 units below. So here's how we're going to add this extra step, because I think this makes more sense to a lot of people. Let's center it where it's supposed to be centered and then see where our mean lies in comparison. So it's really simple in terms of how to do that. What we're going to do first is we're going to say, we're going to take x. Well, sorry, first of all, we're going to create a vector with our original values. So we're going to add one step here. And the way we do this is basically by wrapping this, basically saying store this vector of values into x, and we're just going to type in our original 21, 18, 19, 16, 18, 24, 22, 19, 24, 18, 24, 14, 18, and 15. Okay, so let me just make sure that the mean of those values is in fact 19, which it is. And so all I'm going to do is I'm going to say, all right, now we're going to reassign x. We're going to say into x, store the following. Take x, subtract the mean of x, and then add to that 20, which is the null hypothesized mean. Okay, so we're literally, what we're doing is now if you look at x, these values are still equally far apart from each other, except now they're relative to the mean of 20. So for example, remember 21 was 2 units above the sample mean. Well, now 22 is 2 units above the null hypothesized mean. And similarly, notice that all these values are still equally as distant apart. 19 and 25 was the same thing as with 18 and 24. They're 6 units apart from one another, and so on and so forth. Okay, that's the only extra step that I'm going to add. And now I'm going to run my resample from this because I want to simulate this type of variability, but I want it centered at the null hypothesized value because, right, I assume H naught is true. And if I'm going to do that, then I want to simulate what H naught would look like. So next I'm going to do my X, which is going to be my resample X. X resample. And now I'm going to enter in those values. And one way we could do, I guess we could copy and paste, but I'm just going to type them in. 20, 19, 20, 17, 19, 25, 23, 20, 25, 19, 15, and 16. All right, so I've got those in there. Well, since there are 12 values, we're going to resample 12 values, and we're going to repeat that 10,000 times. So remember, this is like a 12-sided die. You're going to roll the die 12 times, and you're going to repeat that process 10,000 more times, and you're going to compute the mean each time you do that. And so, of course, this produces this matrix. You don't have to look at it every time if you don't want to. Wait, what did I type in? I typed in 12. I did 10,000. No, I'm sorry. It's because I'm repeating 12 die rolls 10,000 times, or maybe I typed in, yeah, okay. So basically now each time we're basically rolling that 12-sided die, and notice that some values can appear 3 or 4 times because you're rolling a die. There's no limit to how many times something can pop up. You can have up to 12 20s, for example. Not very likely, but you can. And so now next what I want to do is I want to run my resample mean, because that's what I really want. I want my resample mean on that vector, so I get my 10,000 means. And the next thing I'm going to do is, first of all, I'm going to close this because I don't need that anymore. And now I'm going to look at the resample hist of x. And so there are all the means. Now notice they're all centered around 20, right? That's because I've rescaled this thing. It's centered at 20. It has a mean of 20. So even if I compute the mean of x, you'll notice that it's almost 20. You get a little bit of sampling variability because it's done 10,000 times, but it's right at just about 20 if you round to 1 decimal place. All right, so now I want to determine, I know my mean, I know where my mean lies. I'm going to copy this, and I'm going to paste it into my, actually this one I want to delete. And I'm going to paste, grab that over here so I could look at it and make some markup on it. And now this guy sent, this is what my null, we call this my null distribution. I'm simulating my null distribution. This is how I would expect the population, the sampling distribution of means to look if in fact mu sub x bar was 20. So what I'm looking at here is I'm saying, this guy is mu sub x bar. Mu sub x bar equals 20, and then of course sigma sub x bar would be whatever the standard deviation of that population is divided by the square root of n. But I don't really care about that. I just want to say, all right, well, when am I going to be convinced this thing is less than 20? well, I don't want to just say, well, my sample mean is 19 and that falls over here and that's smaller than 20, therefore, yes, this guy is producing lean burgers. We're going to say, because we always expect a little bit of variability from one sample to the next. Another sample of 12 steak burgers may produce an X bar of 20.6. And so we want to say, is this sufficiently small enough to where we would say, it's highly unlikely that an X bar of 19 would occur from a population sampling distribution that's centered at 20. Well, you can see that it's not that unusual to get a sample value of that. So first of all, what I'd say is I'd say because we're testing mu is less than 20, we're gonna have some cutoff over here, and I don't know exactly where that cutoff is gonna be because we got to figure out first of all a couple of things. I'm gonna draw it right there for a second. Maybe that's the cutoff, and how are we gonna figure out our cutoff? Well, our cutoff is going to be based upon our alpha level. So let's just say that in this case we've decided to use alpha equals 0.05. Usually we know what we want to test at, which means that this is the 95% confidence level, which means, or sometimes that people call this confidence or significance. So you might say 95% significance level. So that means I have a 5% chance of making a type 1 error. So basically what I want to do is, because I want to see if this mean is sufficiently small, I don't want to test both sides. I already know I don't expect it to be bigger than 20. So I'm going to figure out what my 5th percentile is, and that's going to be my cutoff. If my mean falls below that, my sample mean falls below the 5th percentile, that means it's probably too extreme to have occurred from a population with a center of 20. So what I'm going to do now is I'm going to calculate. I'm going to calculate on that vector x, which contains my means. I want to calculate a percentile, and I'm going to go for the 5th percentile, which is 18.5. So I was close. So what I've concluded is that this should be percent. I've concluded that my cutoff is 18.5, meaning that if I observe a mean that's, if I observe a sample mean that's less than that, then I would probably say, you know what, even though it can happen from this distribution that's centered at 20, it's very unlikely. So I would say reject H naught if my value, if x bar is less than, or we'll say or equal to, because we're saying we want to be 95% confident, so is less than 18.5. However, since x bar is equal to 19, which is greater than 18.5, we basically have no reason to suspect the mean has really changed. 19 is not significantly small for us to be convinced that the whole population will have a mean smaller than 20. Since x bar is 19, which is greater than 18.5, we fail to reject H naught. That is, we want to say we don't believe the mean that mu is less than 20. That's what we said, right? Because we failed to reject this, that means we didn't conclude this. So we didn't say the mean is 20, because just because you can't convict doesn't mean the person is innocent. Another way to say this, and I'm going to have you say this 3 ways, what you're going to do, what that means, and then finally a 95% confidence interval. So what can we say here? Well, if this is my cutoff, that means I'm 95% confident that that mu is greater than or equal to 18.5. We are 95% confident that mu is greater than 18.5, excuse me. So what does that mean? Well, since our mu falls in our confidence interval, then that's a very likely value, right? So since we believe that with 95% confidence that it's bigger than this, that means we do believe that 20 is a very likely possibility. So this is just 2 ways of stating the same thing. In the next video, we'll take a look at another example and setting up these hypotheses and then running through this process. So again, the only thing we're adding is this idea that we're going to simulate the null hypothesized distribution by assuming that our population will have similar variability, but we're gonna center it at the null hypothesis to see if our mean value that we've observed is likely or unlikely given that type of shift and that amount of variability. Now keep in mind, if our distribution were a lot tighter, like, let's say all these values were a lot closer together and we got something like this, then maybe your 95% confidence interval would have been from here on. So you would have said, you know what, 19 is, based on the variability in our sample, it's unlikely that we would get something that small if it were truly centered at mu equals 20. But with this amount of spread, the wider this thing is, the more likely it is to get extreme values.